So shall we start, Dominic? So welcome everybody for this new seminar in the series of the COMSOC video seminar series. Our first speaker is Ashley Piggins, and he will talk about pure strategy Nash equilibrium in the spatial model with Valence, existence and characterization. So Ashley, the floor is yours for 20 minutes.
Thank you very much, Vincent. I will share my screen. If everyone lets me know if they can see it, that would be great. Great. Wonderful. So let me begin. I hope you're all keeping well. This is joint work with Matthew, Zephyrin and Elise. Matthew and Elise work in Cergy, and Zephyrin is in Paris 8. This is a paper on the spatial theory of voting. Okay, so let me start by going back to basics. And the basics really are the median voter theorem, which every student of economics and political science and even game theory knows and loves. We can imagine there are 5 voters here who have ideal points on some left-right political spectrum. And there are 2 candidates who are attempting to win an election, and that election will be decided by majority rule, and the candidates have to decide where to locate on this line. And the voters vote on the basis of the closer the candidate to the ideal point, the better. That's sometimes called the assumption of Euclidean preferences. And then we look, as good game theorists do, for an equilibrium in this location game. So if we're in a situation like this, you've got 2 candidates here. A is located to the extreme end of the spectrum. B is here at Q4's, voter 4's ideal point. And what we can see immediately is that A will get 3 votes, B will get 2 votes, and therefore B will win the election. So I will give B this little cup to denote that B is the winner. However, this situation, of course, as we know, can't constitute an equilibrium because candidate A has an incentive to deviate. If A deviates and moves to the position of voter 3, then A will win by 3 votes to 2. Of course, B is now losing now, and a tie for B is better than a loss. So B again will deviate, and both candidates end up converging on the position of the median voter. And the winner is ultimately decided by a coin toss. So each candidate has a 50% probability of winning. And this is an example of the famous median voter theorem. This is a theorem that's very well known in economics and political science. Now, one of the things that's nice about the median voter theorem is that it doesn't actually matter where the locations of the ideal points are on the line. There will always be an equilibrium. Now, that becomes problematic when we try and extend the argument to 2 dimensions, because the nice median voter theorem almost always collapses when we move from 1 left-right spectrum to 2. So you only need a slightly more general setting for the niceness of the median voter theorem to no longer hold. And this is an example. So imagine that voter 1 is in the middle of the blue circle, and voter 2's ideal point is the middle of the red circle, and voter 3's ideal point is the middle of the green circle. The circles are, of course, in difference curves. And if both candidates locate at the dot, the black dot in the center of the screen there, then there's going to be incentives to deviate. If you look at these 3 ellipses, this one sort of northwest of the point, this one northeast, and this one directly south, if a candidate unilaterally deviates into either of those 3 regions, then that's going to be a beneficial deviation for the candidate, because the candidate is going to get to win the election under the assumption that the election is decided by majority rule. And it turns out that every point in this space has that property. So this is a well-known weakness of the median voter theorem. When we extend to 2 dimensions, we lose the feature that there's always an equilibrium. It's very easy to see that there can't always be an equilibrium, and therefore we want to know what we should do about that. Now, the approach we take in this paper is we follow an argument that we develop an argument that first started in a political science paper written by Donald Stokes. Stokes wrote in 1963. He wrote a famous critique of the spatial model, and he argued that the way politics works isn't in this positional sense, where I have an ideal point, a candidate locates in an ideology space, and we essentially get our rulers out and vote for whoever's nearest to our ideal point. He didn't think that politics was like that, essentially spatial competition. He thought what really happened was that there was what was deciding people's behavior was what he called valence. And so what we do in the paper is we assume that candidate A has a valence, what Stokes would call a valence advantage over candidate B. So we're going to introduce an asymmetry between the two candidates. A has a valence advantage over B. And an example of a valence advantage could be something like charisma. A may be just judged to be more charismatic than B, okay? And things like charisma and honesty and integrity are all part of what Stokes called valences. These are non-positional issues, and Stokes felt that they were decisive in determining voter behavior more than the positional issues. So we're going to give one of the candidates a valence advantage. We're introducing an asymmetry. And the way that's going to work, therefore, in our model is that if I'm voter I and the Euclidean distance between my ideal point and A's location is the same as the Euclidean distance between my ideal point and B's location, then the valence advantage that we're going to confer to candidate I means that I will vote for A and break that tie, okay? So this is one of the things that valence is going to do in our model. It's going to break ties when the candidates are equidistant from my ideal point. There's a second thing that valence is going to do, is that when my ideal point gets close to voter A, then I'm going to vote for voter A regardless of the position of voter B. So this is a sort of, we can think of there being a fixed distance. And if it turns out that if my distance to A is less than that fixed distance, then I'm going to vote for A regardless of the position of B. I'm so close to A that this charisma advantage just drags me in to vote for A, no matter what B does. This is essentially how the valence is going to work in our model. Now, the idea of introducing valence as a potential solution to this problem of non-existence of equilibrium is not unique to us. It was done in this pioneering paper in 2000 on the left-hand side here by Libera and Snyder. And they have a set of very nice results in this paper. And essentially, our model that I'm going to present today is based on their formal framework. But what we're able to do to generalize their results is we're able to go over to the right here to this very nice paper that came out in 2016 that was authored by two of my co-authors and also Craig Tovey, who will be well known to the members of the COMSOC community. This paper on the right solves a mathematical question about the uniqueness of something called the yolk. And very early on in the paper, the authors develop a very ingenious and new way of thinking about the yolk. And what we essentially do in our paper is we take that idea, this alternative characterization of the yolk that appears 2 pages in on the paper on the right, we generalize it and we drag it over to the left and we deposit it in the Libera and Snyder formal framework. And we find that when we do that, that unlocks everything over here. Not only are we able to reestablish all of the theorems in this paper, but we can generalize them to a bigger class of voting games where we may be interested in supermajorities and not just simple majorities. So that's essentially the direction of travel of the paper. Now, let me explain how we do this. So I'm going to introduce the formal model now. It's very straightforward and very conventional. It's just the Libera and Snyder model. So we have 2 candidates, candidate A and candidate B. The candidates have to locate in some m-dimensional Euclidean space. M, that has to be at least a 1-dimensional space. And we have a set of voters who all have ideal points in that space. Now, we're going to endow candidate A with a valence advantage over B, and we're going to measure that by a real number theta. This is the way they do it in their paper, and this is the way, following them, that we're going to model the valence advantage as well. There's other ways you could do it, but we wanted to be consistent with their approach. So candidate A's valence advantage is denoted by this real number theta. And what we assume is that voters have utility functions that have what's termed quadratic loss form. So basically, voter I's utility, if A wins the election, is given by this mathematical expression here. I basically compute Euclidean distance and square it, then negate that, and then I add the valence term theta to it. So this is why it's called quadratic loss. Quadratic because I'm raising to the power 2, and loss because of this negative term. So if A wins the election, this is my utility. And if B wins the election, this is my utility, if I'm voter I, okay? So therefore, if I'm a utility maximizing rational voter, I am going to vote for A if this number is larger than this number. So I can write that out as an inequality, which you see at the bottom of the slide. And then when I rearrange that inequality by taking the right-hand term over to the left-hand side and the left-hand term over to the right-hand side, I can rearrange that inequality very simply as what I have here at the bottom of the slide. Now, what I'm going to do is I'm going to take that and put it onto the top of the next slide, and then I'm going to ask you to dwell on that inequality for a moment with me, okay? So there's that inequality again, written out at the top. Now, if this inequality is satisfied and I'm voter I, I'm always going to vote for I'm always going to vote for candidate A. And I hope you can see immediately from the mathematics there that if the distance between my ideal point and A's location is less than the square root of theta, then it will always be the case that this inequality is satisfied. So we could imagine a world where theta is enormous. And therefore, this inequality is satisfied not just for me, but for everybody in society. And therefore, we're all going to vote for A. And therefore, we trivially have an equilibrium. Because when we're all voting for A, then A has no incentive to deviate, and B has no incentive to deviate, because any deviation by B will still result in B losing. There's nothing B can do about losing. So we trivially have a Nash equilibrium in a situation like that. And it's going to be the case that all equilibria in our model have that property, that A wins and B loses, okay? Because one thing A can always do if A is not winning is deviate and adopt B's location. And thereby, by the tie-breaking rule, everyone will vote for A. So if equilibrium exists at all, it always must be consistent with A winning the election, okay? Now, in this example where theta is very large, we trivially have an equilibrium, but then that begs the following questions, the following set of questions. How large does theta need to be to ensure that there's an equilibrium under majority rule? And the equilibrium we have here is one where everyone votes for A, but how large does theta need to be to ensure that there's A is the majority winner? What about if we looked at a supermajority rule where you need the winner to get 2/3 of the votes rather than a simple majority? And also, can we characterize mathematically the entire set of equilibria? And what we do is we answer these questions for any so-called proper spatial voting game, not just majority games, but games where there may be some sort of quota, some threshold that needs to be met in order to ensure someone is a winner. Now, let me explain our results and how we get those results. So I'm going to give you an example of 3 voters here, and I would invite you to just think of majority voting. So I've got 3 voters here, and these are their ideal points. Now, because there's just 3 voters, we can think of voter 1 and voter 2 along the bottom of the triangle here as a minimal blocking coalition. And what I mean by a minimal blocking coalition is if these 2 voters don't vote for you, you can't win the election. They can block your election. So in a three voter example, there's 3 minimal blocking coalitions. 1 and 2 can block, 2 and 3 can block, and 1 and 3 can block. And these lines connecting the ideal points are the convex hull of the ideal votes of the ideal points of the voters in that coalition. So the bottom edge of the triangle here where there's the line is a convex hull that connects 1 and 2's ideal points. The right-hand edge is a convex hull connecting 2 and 3's ideal points. The left-hand edge of this triangle is a convex hull connecting 3 and 1's ideal point. And the inscribed circle here is known as the yolk. Now, interestingly, there's a standard definition of the yolk, but because of that 2016 paper, I can put that to one side and give you a new definition. The yolk is the smallest ball that intersects the convex hull of every minimal blocking coalition. That's a general definition of the yolk and coincides with the classical definition that refers to median hyperplanes. I don't need that definition here because of this new definition of the yolk. Now, I would like to explain all of our theorems in these two pictures. And let me explain that these two pictures explain everything. Our entire results generalize from these two pictures. The entire case generalizes from the three alternative case. So let me explain what our theorems are in two pictures, and then I am done. So let me take the picture to the left. Now, what I've done here is I've got the original picture I had before, but I've created some rather complicated imagery around it. I would like you to look at the laser pointer I'm showing on the screen. I'm creating a cylinder here that is a set of points in R2. The set is a set of points in the plane that are strictly less than root theta's Euclidean distance from the 1,2 convex hull. So all of the points in that lower cylinder, the interior of that set, all the points there lie less than root theta Euclidean distance from that convex hull. And you can think of a cylinder essentially on the right-hand side, which is root theta distance from the second convex hull, and so on. And then there's another cylinder on the left-hand side of points that are less than root theta distance from the 1,3 convex hull. Okay, so in other words, the circles I've drawn around the voters here are circles with radius root theta. And what you can see immediately on the left-hand side here is that there's no point in the two-dimensional Euclidean plane that exists in all three of those cylinders. And what that means is that there is no Nash equilibrium over here in this spatial voting game with valence. One thing you'll also observe, and this is true in general as well, is that root theta is less than the radius of the yoke. And that's a general result that holds for any game, okay? If root theta is less than the radius of the yoke, you're never going to get, what we call in the paper the b-yolk, there's never going to be a Nash equilibrium, okay? Now, I would like you just to finish to draw your attention to the right-hand picture. The right-hand picture here is identical to the left-hand picture, but what I've done is I've increased the valence advantage theta. So these circles here are now enormous. They're much bigger than the corresponding circles on the left-hand diagram.
Oh, your sun is
and
out.
Now you can see that, that there's a set of points that are common to all three cylinders. And I denote that set of points by E, okay? And E is the set of Nash equilibria in this voting game. So I've increased the valence parameter, theta, and now you can see that these cylinders have points of common intersection. And this is the set of Nash equilibria. If candidate A locates at any point in that set E, candidate A wins, irrespective of the location of B. You can also see on the right-hand side that the circles around the candidates are huge, okay? And that's because root theta now is greater than the radius of the yoke. So what I can do, just to emphasize, is that all of the results you see here for a two-dimensional policy space and three voters and simple majority rule, all the ideas here generalize to all other mathematically possible cases. So let me state our theorems, and then I'm finished. So these are our two characterization theorems. The first says that for any proper spatial voting game, so this is a spatial voting game, AB is your set of candidates, theta is your valence advantage, this is your profile of ideal points, N is your set of voters, and W is a set of winning coalitions that has a certain natural regularity to it. So subsets of winning coalitions are winning, N is always in W, the empty set is not in W. So this is our characterization theorem. This enables me to test whether a point is a Nash equilibrium. So so we have a pure strategy Nash equilibrium if and only if, let me just minimize that. If and only if X's location is less than root theta Euclidean distance from the convex hull of ideal points of each minimally blocking coalition. So this, if you like, is like a litmus test for whether a location by A is going to be an equilibrium or not. And this second theorem is a way of characterizing the entire set of equilibria. The equilibrium set must always be convex, and it must equal this intersection here. This is just like I had in the previous slide. This intersection is essentially E in the previous slide. So these are our characterization theorems, and what we can do is state a existence theorem based on that idea of the radius of the b-yolk that I talked about earlier. We can say for any proper spatial voting game, a pure strategy Nash equilibrium exists if and only if the radius of the b-yolk is strictly less than the square root of the valence parameter. So we're able to characterize the entire set of equilibria, and we're also able to establish an existence theorem that tells us when there's going to be an equilibrium or not, based on this new concept called the b-yolk that we developed from that 2016 paper in Social Choice and Welfare. Okay, that's me. My time is up. Thank you for your attention.
Thank you very much, Ashley. So we can unmute our microphone and give a round of applause to Ashley. So I did not tell you, but of course you know that you have to put your question in the chat if you have a question. So we have Hule, who was the first. So could you remove Ashley, that's good. Could you remove the your slides? Perfect. So we have a first question by Hule.
Yes, hi. That was really very nice. It's more of a clarification question. So you B is the candidate who doesn't have this valence advantage, and you can never have an equilibrium where that voter wins. Does that follow from your theorems? You are muted, so I'm just see you shaking your head. That means maybe no.
No, that's a great question. No, B can never win an equilibrium. Because A could always deviate and adopt B's position. And then because A has the valence advantage, everybody votes for A. So there can never be an equilibrium where B wins.
All right, thanks. And as there's nobody else asking a question yet, let me quickly add one more. When you first kind of informally introduced the model at the beginning, I was wondering, shouldn't the valence be something that depends on the voter, whether they are impressed by that? So would it make sense to extend the model to different characteristics that kind of play a role for different voters? Did you think about that?
Well, that's a great question as well. There's a controversy in the literature about how valence should actually be represented. And so some people argue for something called multiplicative valence. Some people argue for intensity valence, which is perhaps more in keeping with the spirit of your question. We use what's called additive valence. It's very crude and it's very simple. And we essentially do that so that our results can be comparable with Ansel-Libera and Snyder's, who use the same approach. So because we wanted to be able to have in our model comparability with their model, we keep everything about the model the same. And that's why we model valence that way. But certainly there's other ways we could do it, and that would be an interesting thing to do in future.
So now we have a bunch of questions now, but they all are about the same idea about the Euclidean preferences.
Yes. It's a great question.
Matthew is answering.
It's nice to see.
Could I add some detail to that question?
Oh, yeah, go ahead, Bill.
So the mean is the point that minimizes the sum of squared Euclidean distances, and the median is the point that minimizes the sum of unsquared Euclidean distances. So if we're going to be generalizing a median voter theorem, it seems in some ways more natural to consider distance rather than squared distance. And the other question is, of course, if you're doing straight distance, then giving a person a valence is more or less equivalent to having their location be a disk of radius at valence rather than, but if you're using squared Euclidean distance, it's not that simple anymore.
No.
So there's some arguments that one would think would push one towards unsquared Euclidean distance.
Absolutely. And the answer to this, it's a great question. The answer to this is a bit like my answer to Ule's question, which is we were very mindful that we wanted our model to be comparable with the Anselm-Berer and Snyder model. And they're using squared Euclidean distance as well. So it was important for us when we were working on this to not deviate too much from that. So it was purely in the interest of comparability. We thought we want to show that we're generalizing their theorems, and therefore we just wanted to adopt the same formal model that they did. So they use squared Euclidean distance, and this is the reason we do as well. I know that's not a very good answer, but it at least justifies why we took this particular route.
We have a question by Andre Gomberg. Andre, are you here, Andre?
Yes, I'm here. So how would your results relate to a stochastic version of the model, stochastic voting version of the model?
Well, the honest answer is we haven't thought of stochastic voting. I know those models are common in political science and they're well developed, but we just have a purely deterministic model. We're just trying to create, if you like, a baseline model where we can exploit this new idea about the yolk to try and generalize these results in that 2000 paper by Anselm-Berer and Snyder. And we're not thinking really that much about a model of stochastic voting. I mean, it would be a very interesting extension, as would thinking about different formulations of valence in the model, going beyond additive valence. And also, to get back to Bill's point, a model where we did things in terms of Euclidean distance rather than squared Euclidean distance. But I suppose my answer is a bit like my answer to those earlier questions, is we were motivated more by a concern to be able to compare theorems across papers, rather than generalizing in attractive ways in this original paper. But certainly these are things we can think about in future. We didn't pay any attention to the idea of stochastic voting. We just have a purely deterministic model, essentially because we just wanted a sort of baseline model. We didn't want it to be too complicated.
That would kind of respond to the first question, having be occasionally winning. Yes, those models would allow for both sides to win.
Yeah, that's a good point. Yes. Thank you for that. I didn't see that observation. But in a stochastic model, yes, you would then potentially have a situation where B winning could be an equilibrium. Yeah, thank you for that. I hadn't seen that. Yeah.
Okay, so if there's no other question, just looking for a last moment, no other question. So if there's no other question, we can thank again Ashley.
Thanks, everyone.
And we could move to the virtual break. So now we are moving to the second talk, and our second speaker will be Aris Filos-Ratsikas from Liverpool, and he will talk about distortion information trade-off in social choice and matching via queries. So Aris, the floor is yours.
Yeah, thank you very much, Vincent. Let me share my screen. So hopefully you can see the presentation. So yeah, thanks a lot. And I would like to thank the organizers for giving me the opportunity to speak at the COMSOC seminar. The results that I will present today are from two recent works with the same set of co-authors, namely Yorgos Amanatidis, Yorgos Birbas, and Alexandros Voudouris. And they are about the trade-offs between the distortion and the amount of elicited information in social choice and matching. Now, if you're frequent attendees of this seminar series, you might have seen talks on the distortion before. There were at least a couple in the past, but if not, that's absolutely fine because I will give a soft introduction to the topic anyway. So let me start with a motivating example, and this is a completely hypothetical scenario that we have here. So let's assume that the organizers of some online seminar series on computational social choice would like to decide the best talk of the day. And as it happens to be, there were two talks. One was on the distortion in social choice, and the other one was about Nash equilibrium voting games. So how did they decide to do this? Well, they asked each one of the attendees to declare which one they preferred. And the one that was the most popular in terms of the preferences was the one that was selected as the best talk of the day. Now, this is a hypothetical scenario, so let's also have some hypothetical results. Well, it turns out that the distortion talk won by a very, very close margin, 51 votes over 50. Now, let's assume that the organizers, instead of just asking for the preferences, they also asked each participant to just write a short sentence explaining their choice. And now I will give you those sentences, starting from the people that voted in favor of the distortion talk. So the first person said these were equally good. I have a slight preference for the first. The second person said the first one might be just a little bit better. And generally speaking, the first people were they echoed this sentiment of indifference until the last person that voted for the distortion talk. That was probably Alexandros Voudouris that said, I'm an author of the distortion paper, so I have to vote for that. But actually that one, the other one was pretty good as well. Now let's see the sentences written by the people that voted for the Nash equilibrium talk. The first person said that that talk was much better, actually. And the second one said that, what is this distortion nonsense? I don't like this. Game theory is great, so let's vote for the game theory talk. And so on and so forth until somebody said, well, I don't like these talks that use these meta examples as motivation, so I voted for the Nash equilibrium talk. So what am I trying to say here? What I'm trying to say is that this decision was made based on just the preferences of the participants over the two choices, and it was obviously the wrong decision. So a little bit more generally, what I'm getting to here is that when the decision is based only on ordinal information, so information about the preferences comparing the different outcomes, it may not actually reflect the opinions of society. And a little bit more concretely, in a utilitarian social choice, we make this assumption that these preferences and the intensity of those preferences is actually captured by what we call cardinal valuations. And what is this? These are just numerical values that the participants assign to all the possible outcomes, and these indicate not just which outcomes they prefer to which, but also by how much. Of course, a natural question here is, why not just ask for these values then? Well, the point is that it's arguably hard for people to come up with these numerical values. It's cognitively quite demanding. On the other hand, it's arguably much easier to come up with rankings over all the different outcomes, which we call ordinal rankings. And this is actually what people do in many applications routinely. So this is much more conceivable as an elicitation device. And the general question of the distortion literature is, how much worse can the decision be that we make based on the ordinal rankings compared to the fully informed one? So let me move on to the setting. And here we have a set of agents and a set of alternatives. And although I will be using the terminology from voting, just keep in mind that this can be a decision-making scenario. It doesn't have to be an election necessarily. As I said, the agents have what we call cardinal valuations, numerical values for the alternatives expressed by this amount here, VIX. And induced by these values, we also have the ordinal preferences that indicate which outcomes are preferred to which. And an ordinal mechanism, and sometimes also called the voting rule, a social choice rule, a social choice function, is just a function that maps these preference rankings to a single winning alternative. Actually, this is the definition of a deterministic ordinal mechanism, and most of the mechanisms that I will be presenting today will be deterministic. However, I will also be mentioning randomized mechanisms, and there, the only difference is that the outcome is not a single alternative, but a distribution, probability distribution over the alternatives. In utilitarian social choice, the objective is to maximize the social welfare, which is the sum of the values that the agents have for some alternative. And this is very much an objective of a cardinal nature. As you see there, it's a function of the cardinal profile, and we do not have access to that. We have access to a sort of a skewed version of that. In this particular case, just the ordinal preferences, which are consistent with this. And we want to see how well we can approximate this objective. And this is measured by the notion of the distortion. So the distortion of an ordinal mechanism is defined as the worst case over all possible inputs to the problem of the maximum welfare that can be achieved on this instance over the welfare that is achieved by our mechanism. And as you can see here, the input to the mechanism is not the valuation profile, it's not the numerical values, just the ordinal preferences that are induced by these numerical values. So the mechanism operates under much limited information. So in this setting, this notion was defined by Procaccia and Rosenstein about 15 years ago now. And it's similar to other notions that you might be familiar with, like the approximation ratio, the competitive ratio, the price of anarchy in game theory, and so on. Of course, it can be defined for other objectives, but here we will only talk about the social welfare objective in this presentation. So what was known about this? So we did have some results. For ordinal deterministic mechanisms, it was proven quite early in this literature that plurality, a well-known voting rule, is the best thing that one can do, and that distortion is quadratic in the number of alternatives in the asymptotic sense. Randomization helps a lot. We can get to much better distortion bounds. It was proven by Boutillier et al. That you can get a square root of m distortion, more or less, using randomization. Importantly, these results need to assume a normalization of these values. They can be arbitrary numbers, but not exactly arbitrary. They have to be unit sum normalized. That means that when we look at an agent and we look at the sum of that agent's values for the alternatives, that sum is 1. If you don't have any normalization, then it's not hard to see that there's not much that you can do in terms of the distortion. You cannot prove any meaningful distortion bounds. However, for the results that we're presenting today, we don't really need the unit sum normalization. For most of them, we don't need it. Okay, so there's a lot of work on the distortion. I just included one slide just listing papers, trying to convince you that this is important, but that's all I'm going to say about other work in the interest of time. And I will move on to this slide that is about the amount of information that is used in the distortion. So if we have complete access to the cardinal values, the numerical values, then the distortion is trivially 1. On the other hand, most of the work assumes that we have access to the ordinal preferences. And there's also some work that assumes access to limited ordinal information, meaning that perhaps you have information about a truncation of the preference rankings, maybe the first k positions or something like this. What we're interested in is actually this part of the axis. What if we have the ordinal preferences at our disposal, but also we have just some limited cardinal information? And here the motivation is the same, that it is perhaps not cognitively too demanding to ask agents to provide just a few, just a little bit of information, cardinal information, if that can have wondrous effect on the distortion that we can achieve. And we want to study that and explore that. I also have to mention that our work is not the first one to consider this part of the axis. It was considered in different contexts before. And that last paper there by Abramovich, Ancelovich, and Zhu was presented by Elliot Ancelovich in this very seminar several weeks ago. And then there's also an honorable mention, two papers by Mandal et al. And I say honorable because it doesn't really fit this axis, information axis. There, the point is that you want to see the trade-offs between information and distortion in the sense of how many bits are communicated by the agents to the mechanism, and those bits can contain ordinal or cardinal information at the same time. Okay, let me now tell you what we are proposing to do. So here we will elicit the cardinal information via a query elicitation device. In particular, we will have two types of queries. The first type is a very simple value query. It inputs an agent I, an alternative X, and then the result of the query is just the value of the agent for that alternative. And it doesn't have to be exactly the value. It can be some sort of small errors are allowable. The bounds don't really change. And then we have another type of query, which I consider to be much more conceivable as a elicitation device. This is called the comparison query. Here we have an agent. We have two alternatives, X and Y, and some number D. And then the question to the agent is your value for alternative X at least D times your value for alternative Y or not? So the answer is either yes or no. There is less information communicated in this query. And we would like to see what happens if we use those queries too. So in terms of the mechanism, now a mechanism consists of a query algorithm and a modified voting rule. The query algorithm uses the ordinal preferences, gets some answers to the queries, and then the whole information is used by the voting rule to come up with the winning alternative. And the goal that we have is to see how much we can improve the distortion, and what is the the number of queries that we need to ask in order to get some meaningful improvements. And I remind you that these are the bounds that we're trying to beat. This is for deterministic, and remember the square root of n bound that is for randomized mechanisms under normalization. Let me give you the first idea, the first thing that somebody could think of. And here, we can just ask the value of an agent for the lambda top alternatives. So we just find the lambda top alternatives and we ask that value. Then what we do is that we return the alternative with the maximum revealed social welfare. This is just the social welfare according to the things that we have learned. We do get some improvement in the distortion, but it's not great. And actually, what it means is that in order to get to any meaningful distortion bounds, you need to ask a lot of queries. So this is not really what we want. And the title of this slide is actually a Greek expression. It's a translation of a Greek expression that basically means that we haven't done anything significant here. And the reason is that for the lambda top alternatives, we learned a lot of information. We basically learned everything. But the remaining part of the value of the agent, we didn't learn anything. In this part here on the right, we only have the ordinal preferences as before. So really, we didn't do much. The idea is that we don't have to learn that much on the left, so maybe we can reserve some of the queries to learn more on the right. And this is exactly what the next mechanism that we propose does. So it starts by learning the value at the first position of an agent, asking a query. And then it defines some threshold values. And first, it's finding the alternative, the last alternative in the preference of the agent that has value, for which the agent has value vi star over alpha 1. And that can be done with binary search using a logarithmic number of queries. Then we do the same thing for the next value and so on and so forth. And we basically approximate the valuation function of the agent by a step function like this. Then what we do is that we compute this simulated valuation function, and then we return the alternative with the maximum simulated social welfare. And if we set the thresholds in an appropriate way, then we can get this theorem. That is a much better trade-off. And if you cannot parse exactly what this theorem says, let me just give you the interesting corollaries. It says that using a logarithmic number of queries in the asymptotic sense, we can get to the desired square root of m distortion. This is actually matching the best possible distortion of ordinal mechanisms. And those use randomization and normalization. We don't use either of those. So it's in a sense preferable to ask log m cardinal queries rather than use randomization or normalization, or at least it's at least as good. And the other very nice corollary is that if we ask log squared queries, we can get to a constant distortion. And in fact, we can get as close to 1 as we want with the same number of queries asymptotically, which is completely impossible if we don't have any cardinal information. A nice observation is that if we look at how this mechanism works, it actually, once it finds the value of the first position, then it can be run just with comparison queries. And the question is whether we can learn the first position, the value of the first position, or a good approximation using only comparison queries. And the answer is yes, but we need to assume some normalization. So if we assume that we have unit sum valuations, then we can construct a modified version of the same algorithm that achieves a distortion, a constant distortion using a log squared number of comparison queries per agent. So that's even stronger. So let me mention some lower bounds and open problems, and then I will spend a few slides talking about the matching problem, which is a related problem. So the lower bounds that I'm presenting here are, some are from the paper and some are actually from ongoing work. So the second lower bound basically says that it's not possible to get to a constant distortion using a constant number of queries. The first lower bound is says that if we have a constant number of queries, lambda, then we can only get to the lambda root of the number of alternatives as a distortion. And here an interesting open problem is whether we can get to the desired square root of m distortion using only a constant number of queries. We can get there with a logarithmic number of queries, but can we get there using a constant number of queries? And our conjecture is that you can actually do it with 2 queries. We have been trying to prove that this seems to be rather elusive. Let me also mention some interesting research questions before I move on. So the first one is, what if we use randomization? That could be either in the query phase or the aggregation phase. Maybe we can get significant improvements. And of course, we can try to apply the same principle in other settings. The metric social choice setting, for those of you that are familiar with distortion, is actually a very good candidate, but there it will be challenging because the bounds are already small constants, so improvements will be challenging. Now I'm going to talk about the second problem that I would like to talk about, and this is the one-sided matching problem. This is a classic problem in social choice theory as well. It dates back to the paper of Hilland and Zeckhauser in the late 70s. Here we have a set of agents, a set of icons. Every agent has a value for each item. And then the goal of the utilitarian version is to find a matching that maximizes the social welfare. The bounds that we're trying to beat here are quantitatively very similar to the ones that we had before. And these are actually the bound on randomized mechanisms is by a paper that I wrote in my PhD. That was one of the first papers that I wrote. And these bounds need to assume the unit sum normalization as well. We will not assume it for most of the results that I will present. The main idea here is that the same kind of idea works. So we call the same sort of mechanism the K-threshold step function. This is a better name. I take credit for the bad naming of the mechanism in the social choice setting. We can do some modification and the same idea works. And in fact, it achieves very similar bounds, and we can match the best possible distortion of ordinal mechanisms using both randomization and normalization. We don't have to use either of those, and we can get to the square root of n distortion. Again, we can get to constant distortion with a log squared number of queries. And as a matter of fact, this sort of idea can be applied more generally to many other graph problems. General graph matchings, two-sided matchings, resource allocation, clearing exchanges, kidney exchanges, and many others. So if you have a graph problem that sort of can be expressed in terms of preferences, it is likely that this approach can actually work. So it's very, very general. In terms of the lower bounds, we also have very similar lower bounds quantitatively. And here, the open problem is the same, but I'm happy to announce that we have managed to prove the conjecture in this case. So the matching setting is much more structured. So it allowed us to come up with an algorithm that can get to the square domain distortion using only 2 queries, which is, in a sense, if you ask me, rather impressive that you can do that. We don't need to have any normalization. We don't have to have any randomization. So the first attempt was in AAAI 2021. We didn't quite get there. We also needed to assume unit sum normalization. The algorithm that we designed was the mechanism was sort of complicated. And then in ongoing work, we have a better version that doesn't need to assume normalization. It achieves the desired bound. And it's conceptually simpler, I would say. So in terms of the open problems, I guess we have proven the conjecture, but can we actually get tight bounds based on the lower bounds that we have there? So I have 2 more slides to conclude. So the first one is, I guess what I would like to say is that what we're proposing here is, in a sense, a new agenda. It's sort of an extension of the original distortion framework. And we're saying that if you have an interesting social choice problem in which you can define preferences, you can define the distortion, you can study the trade-offs between the number of queries and the information required. And more generally, you can think of different types of queries or different ways of eliciting the information. And let me conclude with some blatant advertising, if you don't mind. So last year, together with Elliot Anselevich, Nisar Ksach, and Alexandros Voudouris, we held a workshop on the distortion and the trade-offs between information and efficiency at EC. There were some very nice talks there, introductory talks, also talks on some papers. I would advise you, if you're interested, you can go there. You can check the talks there, all recorded, and you can access them on YouTube. And another piece of advertisement, we have an upcoming survey. We're writing it at the moment with the same set of people. And we believe that it should be uploaded to archive early next week. That's all I had to say. Thank you very much, and I'll be happy to answer questions.
Thank you very much, Aris. So you can unmute your microphone and we can give a round of applause, please. So the chat was quite active.
Okay.
Let me go up.
Let me check it as well.
So we have first question about cardinal utilities by Mark, but did you get your answer in the talk, Mark?
Yeah, I mean, I guess that's okay. It's fine.
Okay. Yeah, I think it was clear. Ola, you had a question and some answers. Let's see about the number of queries. And Ola?
Yeah, it also has been answered. In the
Yeah,
chat.
it has been answered in the talk.
I guess I have to thank my co-authors and probably some other people that work with the distortion for answering some of these questions already. I see there is a lot of discussion in the chat already. Yeah.
Eden, Peter, you're satisfied with the answer? Yes.
Yes, it was also answered. The queries are adaptive, as illustrated by the use of binary choice, binary search.
So we're just left with Bill's question. Bill?
Okay, so the question is.
So
Yeah,
I think you can see the question. So
I can see it. Yeah, yeah. Yeah. So so the assumption is that they're actually normalized according to unit sum. It's not like we normalize it and then we run the algorithm. So the assumption, which we don't really need for our results because we elicit cardinal information, but for the purely ordinal results, if you don't assume that the normalization is there, you can construct examples for which any ordinal mechanism cannot have a reasonable distortion. It doesn't matter if you normalize and then you do something. It really, when you compare to the original values, then the distortion bars will be quite large.
And instead of looking for the sum of utilities, we looked at the Nash product. Does this solve the problem of needing to normalize?
That's a good question because usually the Nash product doesn't require normalization, right? The problem with this is that with a Nash product, if you don't satisfy one person, then you get a very bad, you will get a Nash product of 0. And sometimes when you only have ordinal information, this might have to happen. Whereas in the utilitarian sense, when you have the sum, it's okay if some people are not really happy. You can still, maybe you can capture the get a sort of a large enough welfare. What happens with other objectives is actually a good question, and it hasn't been studied enough. So maybe there are some settings in which it makes sense, and you can. I know that in the metric setting, there are some works on the max cost or the median cost or some other objectives, but here it's mostly the social welfare.
Is there any other question? I may have one, and it may be a naive one. I'm not a specialist of this literature, but I guess you're always looking at the worst case scenario. Have you think about average scenarios or stuff like that? Is it that terrible?
Yeah. No, that's a very, very good question. Yes, indeed, we're looking at the worst case scenario. And I think we shouldn't. I mean, we should, but we shouldn't only be looking at the worst case scenario. I think in this survey, which we are still writing, today I was planning to write something like looking at something that is more close to the average case is something that we should be doing. As people
I remember some papers by Toby Walsh.
Yeah, so there are some works on this. Even this paper by Boutillier et al. Has done quite a lot of good work in the sort of the average case, but there's still a lot of work to be done.
Okay, so maybe you can, in most of the case, achieve one in less than very, very quickly. Okay.
Yeah, so I guess the point here is that if you just look at some average case, very naively, maybe draw from uniform distributions or something, maybe it won't make that much difference what you do. The distortion will be low anyway. So maybe you need to come up with some sort of setting where it makes sense to start comparing things. But I also agree that, this sort of blanket results that in the worst case, you get M squared and plurality gets it. Maybe, that doesn't mean that plurality is the best thing we can do. Maybe there is something better if we restrict the number of alternatives or we make some distributional assumptions or something like this. So it's worth studying, definitely, yeah.
Okay, thank you. So if there's no other question, we can upload again Aris and his co-authors. And we have some announcements to close the session. So first, the next seminar. So the next seminar will be on the 3rd of March. It will be a session chaired by Jérôme Lang, and he has invited Rohit Vahish from Mumbai, who will speak about stable fractional machine. And the second speaker will be John Dickerson from Maryland, and we don't know yet what will be the talk about. And that's it for the next session. And we have an announcement by Hulu also.
Yeah, so so the next session is on the 11th of March. That's what it says, I think, on the website.
Oh, yeah, yeah,
3
yeah,
is
sorry.
the number indicating the month. Yeah.
So, yeah, sorry.
Okay, and then I wanted to announce, and some of you have seen it already, in April, we are switching to Fridays, and the first April session will be on the 9th. And that one will be a rump session, which many of you know what that means. So it means we're going to have 8 speakers, just giving very short talks of around 5 minutes. If anybody's interested, on the website, you can fill in a small form to give one of those talks. We have half of the slots filled right now. So anybody who's interested, please do that. It's always nice. And this is definitely great for students. It's also definitely wonderful for retired professors. I see some of them here in front of me. So anybody who wants is very welcome to do that. So I'm looking forward to that as well.
Thank you, Ole, and thank you for correcting my mistake. And so the session is over, and we hope to see you in 2 weeks from now. Bye-bye.
Bye-bye.
Bye.
Bye, everyone.